Hey, today we'll be modeling optimizations and solving problems of optimization. Sounds like fun? You bet. Optimization involves putting what we learned last time about maxima and minima and put it into use. Okay? So if there's anything that confuses you or that you don't understand fully, you should go back and review the relevant section. Optimization and its process is about finding the global or local maxima and minima, which can be actually very useful and very important in real life applications. You'll see that in some of the examples we'll look at today. We'll look at 6 examples, and let's get right into it. Okay? First, as a simple review, we'll put our knowledge of the first and second derivatives to a little test. One cool thing that we can do now that we know everything we need to know about first and second derivatives is that we can estimate a graph with just a few pieces of information given about a certain function about its first and second derivatives. Okay, for example, problem shown right there. Take a little time to absorb the information and read it. I'm going to choose which pen to use and go with blue as usual. So let's look at each pieces of information by itself. Okay, the first piece of information is that f prime of x equals 0 at x equals 5. Okay, this means that at x equals 5, the slope is 0. Why do I have a z there? I have no idea. Is 0. Okay, the slope is 0. And then we have 2 pieces of information. F of x is less than 0 when x is less than 5. F of x is greater than 0 when x is greater than 5. So we have these pieces of information, and what we have to notice is that we learned from the last lecture that when the f prime changes sign, it means that it tells us about the concavity of the function. So it changes from being negative to positive around x equals 5. So it means that, f prime changes sign from negative to positive. And that means that it is, think about it, the slope is negative, and then it changes to positive slope. It means that it is concave up. Concave up. Okay? Okay, let's look at the other information about the f double prime. So f double prime equals of x equals 0 at x equals 8. If this were positive or negative, we would know the concavity right away, and that would be somewhat convenient. But we already know the concavity of the function. So let's see where this takes us. Usually, when f double prime of x equals 0, it is an inflection point. But let's see if that's true. Okay, f double prime of x is greater than 0 when x is less than 8, and f double prime of x is less than 0 when x is greater than 8. This means that, again, the f double prime changes sign, and this means that concavity, f double prime tells us about the concavity. So this means that when it changes sign, this means that the concavity changes. Okay, so it is on when a concavity changes, it is an inflection point. So let's try to draw this graph. We have interpreted all the information. We need to draw this graph. Let's draw a nice big graph. So let's say we have our 5 here and 8 here. Okay? So at a certain point around 5, we have a local minima. Okay? Because it's concave up, right? It's concave up, bending upwards. It means that we have a local minima at x equals 5 because it is a critical point where f prime equals 0. So the slope is negative when x is less than 5 and then changes to positive after 5. So it would go something like this. Right? It will be a parabola-looking thing. And at x equals 8, something interesting happens. We have an inflection point. Right now, the curve is bending upwards, concave up, right? This is a terrible graph, but please just pretend that it's an awesome graph. And then the concavity changes. So far up to this point at x equals 8, it is concave up. Then it changes to inflection point, concave down. So it would go something like this. Okay? And this point would be f equals f of 5. This point would be f of 8. We don't have a specified point for f of 5 or f of 8 for this problem. But if such coordinates, y coordinates, were given, we could have drawn a more accurate graph. It could have been, the similar looking graph going over here as a family of graphs. It will shift up and down if we were given the y coordinates. But I just chose this y coordinates for the arbitrary purpose. But the important thing is that we have a local minimum at this point and an inflection at this point. And whatever the function is, it would look very close to something like this. Okay? It is very cool that we can estimate the graph from a few pieces of information like this. Okay? So this is how you use utilize the information about f function, f prime, and f double prime to estimate its graph.